In this video, we're going to have a look at some more features of probability functions. So you need to make sure that you're comfortable with the preceding video before looking at this one. So just a brief reminder, in the last lecture we introduced the idea of probability functions, which are easiest envisioned with this little diagram. So we've started out with a set of outcomes. And then we have what's called a random variable, which maps each of those outcomes to some set of measurements which we can do. And those measurements are usually something that gives us a real number. And then we introduce the idea of a probability function, which maps us to the probability space. And those are usually a real number between 0 and 1. And they give us the probability of any particular measurement being made. So just to have a concrete example to work with for the rest of this section, we're going to look at the case of rolling 2 dice and finding their sum. So if we think about if we want to roll 2 dice and find their sum, our set of outcomes, we could say, is the set of all pairs AB, where A is the outcome of die 1 and B is the outcome of die 2. So for example, we might have something like 1, 1, which says that I got a 1 on the first die and 1 on the second die. And then if we think about the set of measurements that we can do, now here we're wanting to find the sum of the dice. So the possible values that we have here, if we're adding the sum on the faces of 2 dice, would be 2, 3, 4, and so on up to 12. So in this case, if we had rolled a 1 and a 1, then our sum here would be 2. And now if we have a look at the probabilities, as usual, our probabilities are going to be between 0 and 1. And we could ask the question, what is the probability that we got a sum of 2? And in this case, and we'll see how to do this calculation a little later, the answer is, the probability is 1 over 36. And in fact, if you would like to see the probability of any particular sum, we could plot a probability function. So for our die experiment, it's this. So here we're looking at, so this x is the possible sum, and over here we've got our probability. So you can see that the probability of getting 7 is the highest probability. And that's, if you think about it, makes sense because that there's the largest number of combinations of sums of die rolls that will give you a 7. If you want to see this probability function written out as an actual function, here we go. And you could take a little time to figure out where each of these sums comes from. It's pretty straightforward. Okay, so that's what we're working with. And we're going to have a look at some ways in which probability functions make our lives easier when we're thinking about random variables. So to give some idea of what it is that we're going to do, let's have a look at some examples. So you've already seen this problem and probably worked out the solutions to A, B, C, and C, but here's the kind of question that we'd like to also be able to answer. If the experiment of choosing 2 balls from the urn were repeated many times over, so let's imagine we're thinking about 100 times, what would be the expected number of blue balls that you get? So we're thinking we've got this experiment, we've got an urn with 5 blue and 7 grey balls, and we're going to take 2 at random, and that's going to be our experiment. And if we did this 100 times, we want to think about how many blue balls overall would we choose. And now you don't want to have to model this with a tree diagram. That would just be crazy. So we'd like to be able to find some quick way of answering that question. Another question we might ask is, if you flip a fair coin 3 times, how many heads do you expect to get? And again, you could model this using a tree diagram, but if you then wanted to extend this and say, okay, if I did this experiment 100 times, how many times would I expect that heads would come up? And you again would not want to have to do this with a tree. So having some quick way of measuring would be good. And just a third example that we're going to look at. Suppose a student takes a 3-question test and has a probability of 0.8 of getting any question right, regardless of what they did on any other problem. What we'd like to know is, what mark would we expect the student to get if each question is out of 2? Again, you could do this using a tree diagram, but we'd like to build up the tools to be able to do this a little bit more quickly. So we're going to start with another definition and bring this in as we go along. A value function assigns a numerical value to the outcome of a measurement. So if we're thinking about our standard setup, we've got our sample space and our random variable that's taking us to some measurement, and that measurement has a certain probability, but the value function assigns a numerical value to the outcome of a measurement. So I'm thinking about the measurement here, which is my R space. So over here, I've got a value function, u of x, and this gives me a value for each measurement. And you might be thinking, what on earth is going on here? The best example to think of over here is our test example from the previous slide. So just if we go back to check, we've got a test and a student's answering 3 questions, probability of 0.8 of success on any question, and we'd like to know the mark that they get if each question is out of 2. So in this example over here, we've got our random experiment where our student is getting, for example, everything right, maybe the first 2 right and then wrong, and so on. And then here, our random variable, our R, is measuring the number of correct answers. So no right answers, 1 right answer, 2, or everything right. So that's the number of correct answers. And then our value function over here, our u of x, is the marks achieved. So for example, u of 0, so if you didn't get any correct answers, then you're going to get no marks. If you get 1 thing right, you're going to get 2 marks. If you get 2 things right, you're going to get 4 marks. And if you get everything right, you're going to get 6 marks. So we have our number of correct answers is the range of our random variable, and to each of those possible numbers, we assign a value function. So now that we've introduced this idea of a value function, what can we do with it? Well, the idea is that we would like to find the expected value of this value function. And it turns out that the way that we do this is by combining our value function and our probability function in a sum. So just to fill in what each of these things is. So we've got our random variable x, which we know over a space R, and we've got a corresponding probability function that we've seen before, and the value function u of x that we've just seen, which attaches a value to each value in R. And the expected value of our value function is given by this formula over here. So here we've got our value of our random variable measurement. So for example, that's the number of marks that you get for a particular number of correct answers. And then we've got a probability of our random variable measurement. So in our example, the probability of getting one correct answer was 0.8. So we need to figure out the probability of, for example, getting 2 right answers and 1 wrong. So we need to figure that out. And then this x in R, we're going to work out the sum over each possible measurement. And just a reminder here, so we're saying the expected value of our value function. We don't need to worry about this bit because this is continuous. So if you're interested, this is how we define it if you've got a continuous random variable, but we will be working with the discrete version. So what does this all mean for our intuition? Let's go back to our very simple example. We're flipping a fair coin 3 times, and we'd like to know how many heads do we expect to get. So we're going to work through this example in a lot of detail and hopefully clarify what each of these things is. So the first thing is we want to know how many heads do you expect to get. So we want the expected value of the number of heads. So we want the number of heads to be our value function. But in fact, the number of heads is just going to be our random variable. So here we're going to have that our value function is just equal to the random variable. We'll look at a slightly more complicated example after this. So let's map everything out. So let's start out with our sample space. Well, here we've got our sample space. We're flipping a fair coin 3 times, so our possible outcomes are heads, 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 tails. We could keep going, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. And if we think of these are each equally likely. And now we want to think about what we're measuring. So we've got our random variable, x. So what is that space? Well, we're measuring how many heads. So our random variable, we can either get none, 1, 2, or 3. So remember, this is the number of heads possible. So for example, if we were to look at our random variable here, this would give an r is equal to 3 because we've got 3 heads, whereas, for example, over here we'd have r is equal to 2. Okay, and now we want to look at our probability function. So we head over here to our probability function. Now remember, our probability function is going to look at each element of a random variable and tell us the probability of getting that particular measurement. Well, we know that each of the outcomes in our sample space are equally likely. So we can think about what is the probability of getting 0 heads. Well, there's only one case in which that happens, so that must be 1 over 8. That's when we get all tails. Similarly, I'm going to put this further down. What's the probability of getting 3 heads? Well, that's when we get heads, heads, heads. That's the only outcome that gives us 3 heads, so that's going to give us 1 over 8. If we want to think of the probability of getting 1 head, well, let's have a look. We've got this case over here, and this case over here, and this case over here. So that gives us, each of those has a probability of 1/8, and we've got 3 of them. So that's a probability of 3/8, because any one of those will give us a random variable of 1. And then finally we can ask, what's the probability of getting 2 heads? Well, the remaining cases are these 3, so again we have 3/8. So our probability space has 4 entries. It's got, our probabilities are 1/8, 3/8, 3/8, and 1/8. And if we wanted to sketch that, just so that we could get a feel for what our probability function looks like, it would look like this. So this is my random variable. Possible values for that are 0, 1, 2, and 3. And I'm going to have probabilities. So this is my f of x. And here I've got my probabilities. My probability of getting 0 is 1/8. Probability of getting 1 is 3/8. Probability of getting 2 is also 3/8. And probability of getting 3 is 1/8. So this is what my probability function looks like. Now let's go back to the actual question that we were asking, which was, how many heads do we expect to get? So we want the expected value of the number of heads. Our value function is simply going to use our straight random variable. So we have our value function of 0 is just 0, value function of 1 heads is 1, of 2 heads is 2, and of 3 heads is 3. So we'll see an example where these are different in a little bit. For the moment, let's just work with this. Okay, so now we want to work out the expected value of our u of x. So we want the expected value of u of x. And our formula tells us that we've got to sum over each of the possible values of the random variable, the value of the value function for that particular element times the probability of that element. So in this case, because we have a nice simple value function, we're going to have just the possible value times the probability of that. And notice over here we're just going to be summing over 0, 1, 2, and 3. So if we do that, we have, if we get no heads, the probability of that time is, we're going to multiply that by the probability of getting 0 heads, plus 1 times the probability of getting 1, plus 2 times the probability of getting 2, plus 3 times the probability of getting 3. Plugging in our probabilities, and if you sum that all up together, that gives you 1.5. So this might seem a little bit strange, and this is one of the things about expected values, because this is saying we expect 1.5 heads if we flip a coin 3 times. And we know that you can't actually get 1.5 heads. You could either get 1 or 2 or 3 or none. But this is just saying if you did the experiment of flipping a coin 3 times, and you did that experiment many, many times, on average you would get 1.5 heads. So let's have a look at a slightly more complex example. So we're going back to our student taking a 3-question test. And they have a probability of 0.8 of success on any question, regardless of how they did in any other problem. And we want to know what mark they would get, assuming each question is marked out of 2. So they can either get a 0 if they get the question wrong, or they can get 2 if they got it correctly. So again, let's do some modeling. So we're going to start with our sample space. So our sample space, I'm just going to use ticks and crosses to indicate possibilities. So we've got student could get everything right, student could get first 2 right, last one wrong. Now we're getting first one wrong, then 2 right, wrong, right, wrong, 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 right, and possibly get everything wrong. And the thing to notice here, which is different from the previous example, is that these are not all equally likely. So we can't just say, oh, the probability of each of these is 1 over 8, because we know the probability of getting something correct on any question is 0.8. So we're going to have to do a little bit of work on working out the probabilities. Then we want to think about what is our random variable. Here we're thinking of the number of correct answers as our random variable. So you can get none, 1, 2, or 3. So this is a number of correct answers. And now for our value function assigns the number of marks that the student gets. So the number of marks that a student could get, let's just mark here. So if we think about this, we're going to have, so let's rather write it like so. We're going to take each of the possible random variables. We've got u of 0, so if you don't get anything right, you get no marks. If you get one thing right, then you're going to get 2 marks. If you've got 2 things right, 4 marks. And if you get everything right, then you're going to get 6 marks. And the question is, what mark would you expect the student to get? So we want the expected value of u of x. Okay, well, in order to do that, we're going to need our u of x, because remember, our expected value of u of x is the sum over possible values of our random variable, u of x times f of x. So this we've already got, we've just worked that out, but we're going to need our probability function. So let's work that out. Well, a tree diagram is going to help. So let's think about the first question. You can get the first question right or wrong. I've got a probability of 0.8 for getting it right and 0.2 of getting it wrong. And then second question can be right or wrong. Again, the same probabilities. And finally, third question, again, right or wrong, right or wrong, right, wrong, right, wrong, and you can check these. So if we look at the top, following the top branches, that gives us the probability of getting all correct. Following the bottom branch, this gives us the probability of getting all wrong. And you can spend some time checking, but our probability function, if you get the probability of getting 0, means you're in this bottom branch, which is 0.2 to the power 3, which is 1 over 125. The probability of getting one question correct is 0.2 squared times 0.8, and there are 3 possible ways in which you can do that. So you can get, so we're wanting to get 1 correct and 2 wrong, so that's 1 correct and 2 wrong, 1 wrong, 1 right, 1 wrong, and then our third possibility here is you get wrong, wrong, and right. So that's how we get 3 times the probability of getting 2 wrong and 1 right, which is this over here. And if you work that out, that's 12 over 125. Now we can think about the probability of getting 2 things correct. If we have a look at those, well, we have one option is right, right, wrong. Another option is right, wrong, right. And finally, we could have wrong, right, right. So again, we've got 3 ways of getting this particular combination, and the probabilities are 0.2 times 0.8 to the 0.8 squared. And if you work that out, you'll get 48 over 125. And then finally, we have the probability of getting all the answers correct, and that's just 0.8 cubed times 1, and that's 64 over 125. So our probability distribution for this particular function, for this particular probability function, will look something like this. So our possible values of x are 0, 1, 2, 3, so the number of things we could get right, and the probability function will look something like this. So this is not to scale, but it's increasing as x increases. Okay, so now we have all the elements that we need. We have our value function and our probability function. So we can go ahead and calculate the expected value of our value function. So this is, we're calculating the expected mark, and we know that this is the sum over all possible values of the random variable, our value function times the probability. And remember that our random variable is the number of correct answers, 0, 1, 2, or 3. So we've got the value function of getting 0, which is the marks you get if you get 0, times the probability of getting 0 questions correct, plus the number of marks you get if you get 1 correct, times the probability of getting 1 correct, plus the number of marks that you get if you get 2 correct, times probability of getting 2 correct, plus the number of marks you get if you get 3 correct, times the probability of getting 3. So if we write this all out, we've got 0 times 125 plus 2 marks times 12 out of 125 plus 4 marks out of 48 over 125 plus 6 marks times the probability of getting all correct, which is 64 over 125. And if you plug that in, you're going to get 24 over 5, which is your expected mark is 4.8. So again, this might seem a little bit strange because 4.8 isn't a mark you can actually get on the test. But the idea is that if you repeated the test again and again with the same student with the same probability of getting correct answers, then on average, if you averaged how well the student did in each test, that average would come out to be 4.8. So those are 2 examples of our expected value. What our expected value is telling us is the average value, the value that you would get if you average the results over many trials. In terms of the probability function of the random variable, the expected value kind of measures the center of the function. So we saw in our example the expected number of heads in 3 coin flips. If we go back to that, we got our picture here of our random variable. We saw that our expected value was 1.5. If we plot that over here, you'll see that it is telling us roughly where the center of our distribution is. So that's 1.5. So calculating the expected value for a random variable or a value function tells us that if we were to do the experiment many, many times, on average, we would get the expected value as the outcome. There are a few other useful measures that we use. So sometimes the mean is another term used for our expected value. So we've seen that already. That's the expected value. And sometimes you'll also hear this referred to as the average. So we've seen that already. The variance of a random variable with probability function f of x is given by the expected value of x minus the mean. So the things you want to think about is if we have some probability function, our expected value tells us roughly where the center is. The variance, on the other hand, tells us roughly how spread out the probabilities are around that central value. So you might have a probability function that looks like something like that, in which case the mean would be somewhere there, and the variance is quite small. This is a narrow distribution, as opposed to a probability function which does something like that, again has a mean somewhere there, and it has quite a big spread on either side of the mean. So the mean and the variance are the two things that we need to know for this particular course. For interest, there are some other measures. There's the skewness and the kurtosis. If you're interested, the skewness measures how symmetric the probability distribution is. So you might have a probability distribution that does something like that, or maybe it's very symmetric, or maybe it tends over to the right. And the skewness gives a measure of which of those cases we're in. But as I say, you just need to know the mean and the variance for this course. So let's actually do a calculation. So we're taking quite a small sample space with a random variable so that we can actually do these calculations by hand. So let's have a look at what we've got. So we've got over here, we've got our random variable, and here we've got the probability of each of those measurements. So that's our probability. Okay, so your probability of getting a 0 is 0.1, probability of getting a 1 is 0.25. And this is a bit of an odd space. You can get a 2 with 0.4 probability, 4 of 0.15, and 7 of 0.10. So whatever it is that we're measuring here, the only possible things you can measure are 0, 1, 2, 4, or 7. And if we plot that probability function over here, we've got our random variable on the x-axis, and we've plotted the probability up on the y. So here, we'd like to find the mean, and we'd also like to find the variance. So our mean is defined as the expected value of x. So what we're really doing here is we're saying that our value function is just x. So this is like the first case that we did when we were counting the number of heads when we were flipping a coin. So in this case, we're going to sum over all the possible values of the random variable, the value of the random variable times the probability. And if we do that, we get 0 times 0.1, so that's where we're looking at this, plus 1 times 0.25, oops, sorry, that should be a times, plus 2 times 0.4, plus 4 times 0.15, plus 7 times 0.1, and if you multiply that all together, get 2.35. And if we're plotting 2.35, that will be somewhere around here. It gives us a rough measure of where the center of this distribution is. So this is our mu equal to 2.35. And now we'd like to calculate our variance, which is the expected value of our random variable minus the mean, all squared. And if you go, we'll talk a little bit more about this at the end of the lecture, but it turns out that this is the same as the expected value of the square of the random variable minus the mean squared. And if you work this out, so we're going to work out the expected value of x squared, well, it's going to be each value of x squared, so that's 0 squared times the probability of getting x, plus 1 squared times the probability of getting 1, plus 2 squared times the probability of getting 2, 4 squared times the probability of getting 4, 7 squared times the probability of getting 7, and we're going to subtract off the mean that we worked out before, and that gives us 3.625. And this gives us a measure of how spread out our distribution is. So we can say variance, if we look over here, up to about here is about mu minus 3.6. And that is about our mean plus 3.6. So what this says is that most of our probability distribution falls in this region. And that's what the variance is giving us. It's saying this is quite a spread out distribution. A little further back in the notes, we needed to calculate the variance, sigma squared, which is defined as the expected value of x minus mu all squared. But we actually used this version, which is the expected value of x squared minus mu squared. And it's important to understand why these two are equivalent. So let's check. We're going to start with the expected value of x minus mu all squared, and we expand out the bracket to give the expected value of x squared minus 2x mu plus mu squared. Now let's do a little bit of extra work, and then we'll come back to this. So recall that the expected value of any function of a random variable is given by the sum over the range of the random variable of the function times by the probability function. And this is true for any u of x. So if we think about that, if we had, for example, the expected value of some function u of x plus some v of x, if we wanted to calculate that, we would say, well, this is a sum over the random variable of our u of x plus v of x all times by the probability function. But this is really just, so inside the sum we have our u of x plus v of x all times f of x. But we could rewrite this as the sum of u of x times f of x plus v of x times f of x by distributing the f of x into the sum. And now we can split this into two sums, because this is really just a sum which has a sum inside it. So instead we could write this as the sum over x equals r of u of x times f of x plus the sum as over x in r of v of x times f of x. Which is really, if we look at this, just the expected value of u of x plus the expected value of v of x. Oops, I've got too many brackets there. So we see that the taking expectations distributes over sums inside. So now we can go back to our expectation of all these things over here and say, well, the expected value of x squared minus 2x mu plus mu squared is equal to the expected value of x squared minus the expected value of 2x mu plus the expected value of mu squared. Now the next thing to notice is that if c is a constant, then if we look at the expectation value of some constant times the function we want to find the expectation value of, this is going to be equal to sum over all x in our range of c times u of x times f of x, just by definition of expectation. But this c just multiplies every term that we have here, so we might as well just rewrite this as c times the sum of u of x times f of x. And this, in turn, just gives us c times the expectation of u of x. So we see that if we have constants inside an expectation, we can pull them outside. Now let's go back and have a look at what we've got over here. So our first term is just a straight expectation of x squared. Now over here, we've got a 2, which is a constant, and we've got a mu, which is a constant. So we've got minus 2 mu times the expectation of x, plus, and here we've got the expectation of mu squared, but mu squared is a constant. So we have mu squared times the expectation of 1, and that is just 1, because that's a constant. But have a look what we've got over here. Our expectation of x is actually equal to mu. So what we've got here is the expectation of x squared minus 2 mu squared plus mu squared, which is equal to the expectation of x squared plus, or rather, minus mu squared. And that is how we got the formula that we worked from. So if we head up to here, that's how we got this.